其实咱们从来没有真正去他每次都提说，我们应该参考大理。
Can everybody hear me out there? You good? Last time we talked about computational geometry. We talked about range queries. Range queries is a type of query that asks how many objects are within a certain range. And we said the two-dimensional version is used in databases, and one version of it is geometric. How many points are within a given query rectangle? And we said you can generalize it to 3D, in fact, any number of dimensions, and it's not just about points, it's about arbitrary objects, arbitrary spaces. And we said we first try to solve the 1D version, right, as a general problem solving technique. You can't solve it in higher dimension, try to solve it in lower dimension, you're going to work yourself out to the more complicated case. And we said in 1D you can do it by sorting first as a pre-processing step, then binary search will get you a query, a couple of binary search will get you any window within that. So that was pretty easy in 1D. In 2D it wasn't so easy. It's a generalization of binary search in 2 dimensions. Use exclusion inclusion principle. You compute all rectangles anchored at the origin, and once you have the counts for those, you can do several binary searches and get the right set of triangles to include and exclude and get the count for any arbitrary triangle, rectangle that is. And the inclusion exclusion principle is very general. It comes in handy in many places, not just here, obviously. And so we gave an example of how to do it in 2D. The generalizations to higher dimensions are pretty similar. The complexity will grow with the dimension, but that's to be expected. And we said you can generalize it to arbitrary figures, not just points, not just rectangles, but triangles, circles, half planes. The objects that you're searching over don't have to be points, they can be segments, arbitrary polygons, and so on. That makes it even more complicated. Then we gave an algorithm how to find if you're in the inside or outside a given polygon. So it's a polygon query, interior versus exterior. And it's a point location problem. There's many types of those in computational geometry. And again, it could be arbitrary dimensions, hyperdimensions, arbitrary types of objects, not just polygons or polytopes, which are higher dimensional polygons. But basically, we said that it's an odd-even kind of a test based on the Jordan curve theorem. Whether you're inside or outside, you project the ray to infinity, and if it intersects the convex polygon once, versus twice, versus 4 times, odd number of times, you must have been inside. Even number of times, you must have been outside. And the ray casting direction is completely arbitrary, which is one of the nice things about this. There's a few complications. Some rays can be tangent, or even overlap with one of the sides, or go through a corner. So you have to kind of do some extra tests to figure out these boundary conditions. But aside from those few boundary conditions, this is a very sound premise, and a very sound test for interior and exterior kind of testing. Now, all this assumes that it's a one-shot problem. There's no pre-processing involved. Solve it once. And so this is how you do it. Linear time in each case. But if you allow some pre-processing, obviously it can be better. Just like searching. If you search a bunch of unordered things in a giant set that there's no order across the elements, it's going to take linear time to go through the whole thing. But if you allow pre-processing, you can sort the set and then use binary search for fast searching. Same principle here. So these are generalizations of binary searching. And the pre-processing is sort of analogous to the sorting that you would do in order to enable binary search to begin with. Except it's more involved here. It's not as simple as just plain sorting. So to find out if you're inside or outside, with pre-processing allowed, we said you can divide it into like pizza pies, triangles based on some interior points. It could be the centroids, for example, or anything else inside, or on the boundary for that matter. And you divide it into triangles, and you sort the triangles around that interior pivot point by polar angle. And that's a plain sort step by polar angle. then, once you have a query point, like the red one here, compute its angle from the x-axis, and then do a binary search on the other angles of all the other wedges, and it'll tell you which wedge you're in, and then within that wedge, you can be either in the interior or the exterior of that region, because the wedge, all these wedges are semi-infinite, they're infinite in one direction. So you have to do a little bit of testing once you know what wedge you're in to see if you're inside or outside that triangle in that wedge. And that'll tell you whether you're inside or outside that original blue polygon. So with all that said and done, the query time degenerates to just binary searching, essentially, plus this inside-outside wedge kind of disambiguation, which can be done in constant time because it's a single wedge and a single point, and the wedge is basically a triangle. It goes infinitely in one direction. So logarithmic time per query after n log n time for preprocessing. And I gave a caveat that you have to worry about computational numerical precision. Don't let that get away from you. In some cases, it becomes important. And by that we mean, in mathematics, the square root of 2, when you square that, you get 2. In computer science, we take the square root of 2 and square that, you don't get 2. You get 1.9999 something. So don't underestimate the nefariousness of numerical imprecision to creep up on you and become real significant and completely change your answer possibly from inside to outside. You can count, especially when points are close to boundaries and close up points to each other and things like that. Having said that, the algorithm is pretty sound, and it's based on solid principles of geometry and rationality and logic, so it works pretty nicely. We also said towards the end of last lecture, you can use other wedge schemes. You don't have to use the centroid. You can use one of the points of the actual polygon. If you do that, you get, again, a bunch of triangles. And one wedge, keep in mind, is this outside wedge. That's this complete semi-infinite outside wedge. This is one more big exterior wedge. But given that, you can figure out exactly like before whether the point is inside or outside the polygon by doing a binary search on the polar angles. And then and you have to disambiguate whether you're in the semi-infinite portion of the wedge or the finite portion of the wedge inside the original blue polygon. Anyway, so just so you know, there's lots of kind of slicing schemes that you can do, right? Sometimes pizzas are sliced into triangles, sometimes into squares, right? And it's still the same pizza. And then we generalize it to the non-convex case. Here's where it gets more tricky. I think we left off with this notion here. So this was a 5-minute summary of the last hour and a half. So again, there are lots of pre-processing, and you need to know if a query point is inside or outside some arbitrary polygon. And now it's no longer convex. The convex case in the previous couple of slides was easier. Why? Because you can easily slice it into triangles in a very disciplined, obvious way. And you can sort them by polar angle. Here, not so much. So the pre-processing step will be the following. We'll sort the x coordinates of all the points, left to right. We'll sweep them. A sweep line kind of approach will be very commonly used in computational geometry. So basically then you find vertical slices. You slice it vertically this time through all the x coordinates of all the points. Okay, so every point in the original set of vertices in the blue polygon will induce a vertical slice. Okay, so there are the vertical slices of all the polygon vertices. And then you partition each slice into trapezoids. Trapezoid has 4 sides. Trapezoid is kind of a generalized rectangle where the sides don't have to be parallel to each other, except one opposite pair has to be parallel, the other two can vary. So there's a green trapezoid. There's a red trapezoid that's semi-infinite in the lower direction. That's okay. That's still a trapezoid. 2 parallel sides, and the other 2 sides are unconstrained. In fact, one of them is not even there. It goes down to infinity. That's okay. And you keep slicing each vertical strip into these trapezoids. Nice thing about trapezoids, they only have 4 sides. So you can easily tell if the point is inside or outside the trapezoid. It's a constant time test. How many get that? They only have 4 sides. And, put the right combination of if-then else's together in a nested way, and you'll know if the point is inside or outside. A given trapezoid, yeah.
If it's semi-infinite, like on the lower side, is it still considered a trapezoid?
Yeah, we'll consider that a trapezoid. A degenerate trapezoid where one edge is in infinity for the purposes of this approach or analysis. Just like you can say a quadrilateral has four sides. Quadrilateral is any polygon with four sides. If one of those sides is zero length, what is that quadrilateral also? If one of the four sides of a quadrilateral has zero length, that quadrilateral has degenerated into a triangle, but it's still a quadrilateral, technically speaking. So don't get too hung up about these generalizations of what things are. So a triangle is also a quadrilateral with a degenerate edge as it becomes zero size. If you want to consider it that way. Okay, so back to the vertical slices. You keep doing this. So here's a trapezoid, here's a trapezoid, and notice that in each slice, the trapezoids are completely well ordered, top to bottom. There's the highest most trapezoid, and then the next highest most trapezoid, and then the next one after that. That's not ambiguous. They don't overlap, and they don't overtake each other in weird ways. They're completely well ordered within the strip. How many you can see that? They impose a total order on these trapezoids within each strip of vertical strip. All right, once you've done that, you keep slicing all the vertical strips of trapezoids, and then within each strip, you sort the trapezoids by y-coordinate, by their total order within that strip. So there's a lot of trapezoids floating around here, but they're sorted by x first, and within x, within every strip, they're sorted by the y, which appears first, which second, which third, within the strip. So that's the pre-processing we're doing. It's a lot of pre-processing, but you'll see in a minute why it works so nicely, why we're doing this. So now, you need to do a query. A point comes around, and you want to know if it's inside or outside the original blue polygon. So how do you do that? You take that point, and you see which strip it falls into. And here it falls into this slice, or vertical strip. How do you figure out it's this strip and not this one or that one or some other strip? Binary search. The strips are sorted by their x coordinates, one after the other. It's a total order, left to right, on all the strips. So find out which slice or strip it falls into. And it's this one here. So I'm color coding it purple. It's this one. And then within that strip, find out which trapezoid it falls into. How do you do that? Within that strip that you detected that point falls into, how do you determine which trapezoid within that strip that point falls into? Two words? Binary search again. How many see that? Double binary search. Binary search finds you the strip or the slice, and within that, another binary search finds you the trapezoid. And then you know which trapezoid you're in, and each trapezoid is labeled whether it's inside or outside. All the red trapezoids are exterior trapezoids. All the green trapezoids are interior trapezoids. And by the way, what you said earlier, what we talked about earlier, this is a trapezoid when one of the two sides, one of the four sides became zero length, and now it's called a triangle, but it's still a trapezoid. So it's a degenerate trapezoid here, much like the others. Just this thing here has zero length, if you will. Yeah.
How come you can use binary search to figure out which trapezoid you're in?
Let's dig into that. I was waiting for somebody to ask that. We just said binary search and threw our hands up. But let's dig into the details. How do you use binary search to figure out which trapezoid you're in? Once you know you're in that slice here, that strip, vertical strip, that vertical strip gives you all the trapezoids sorted high to low. How do you know which one you're in? It's not magic. You gotta do some work here. What's the details of that? Sure. Or pick the trapezoid that's right in the middle. They're all sorted high to low. Pick the middle trapezoid. See if the point is higher or lower than it. Well,
Yeah,
first
the
see.
trapezoid isn't a single point on the y-axis, it's like a range.
Sure, but you can tell if a point is inside a trapezoid that you just picked. You just pick the middle trapezoid, see if the point is inside or not. How do you do that? Well, a few if statements will get the job. There's only 4 sides. So figure out if the point is inside that trapezoid. We won't dig into that nested set of ifs. It's not that complicated. Let's say it's in there. Then what do you do next? It's in that trapezoid. You just pick magically. You lock that. It's there. It's inside.
Well, then that's fine, you just check.
Then you just found your answer. See if that trapezoid is one of those red ones or one of those green ones. If it's a green one, you're inside the original blue.
So but if
Polygon.
it's not in there, how do you
It's
know
not
which
in
side
there.
your cursor?
Yeah. If it's not in there, what do you do next? Let's say it's not inside. So it's either over here or over there. It's either above or below it. So you can also tell if it's not inside it that it's above or below it. Right? Because you know what the 4 sides are of the trapezoid, and you know these 2 line segments.
Okay.
Right? For each trapezoid, you know this line segment and this line segment. Like this point is not inside, it's either below this line segment, this red line segment, or it's above this red line segment up here, and you know which. Okay? And if it's above, what do? Take that whole range above, ignore forever the range below, take the mid trapezoid of that upper range, and repeat the whole process. Right? Binary search keeps dividing the space by a factor of 2 every time. And because it divides it by exactly a factor of 2 every time, the space keeps shrinking exponentially. And eventually the space becomes just one object after how many iterations? Logarithmic number of iterations. That's the beauty of binary search. That's what happens when you exponentially diminish something. You can only do it for log times before the something vanishes into just one thing, as opposed to a large number of things that you started with. Right? Same thing when you search a phone book. Same thing when a lot of things in life are kind of binary search type situations. Okay, so 2 binary searches will get the job done. One for finding the original slice, vertical slice, and within that, a second binary search will find you the actual trapezoid. And these trapezoids are pre-labeled from the pre-processing step as interior and exterior trapezoids, and then you'll know. So bottom line is, using all this infrastructure, you solve the problem of given a point, whether it's inside or outside, an arbitrary non-convex polygon. So we generalized the previous algorithm from convex polygons to non-convex ones. Notice all the complexity. Here, it was easy because if the polygon was convex, all you need to do is create triangles, sort by polar angle, end of story. When it's non-convex, it got more tricky. We had to do more pre-processing, and the pre-processing involved creating a lot of vertical strips or slices. Within each one of those, we had to create a lot of trapezoids and sort those by the other order. So slices are sorted by X, and trapezoids are sorted by Y, total orders. And then you do 2 binary searches, not 1, but you get your answer and you get it in logarithmic time still, which is nice. You can't do it in faster logarithmic time based on information theoretic arguments. You can show that any kind of searching in general take at least long time. Very few exceptions. Okay, how many get all this? Pretty straightforward. And we didn't give a lot of pseudocode. In fact, we kind of described it in English and mostly the picture, but the picture kind of tells you the whole story, intuitively what's going on. And if you have to implement this, yeah, you can implement this, fight the compiler for a while, and then you'll win, and it'll work. But that's the idea. It's a beautiful algorithm. Right? I mean, intuitively, it's very sharp. Right? There's no many ways here for things to go wrong or truth to hide and bugs to creep in. I'm not talking about the programming. Programming is always messy, but the algorithm itself is pretty crisp. Question.
I was absent last session, so my question is, can you explain a little bit about the application of the algorithm, like real problem that you can solve with this application?
Oh, sure. So, in fact, I have some drawn up later, but let's say you have a big map of, a country or full of counties in a country or, cities or, property lines, and, you're going with your GPS and you want to know which region you're in. Which county am I in right now, or which property line am I in right now, and you want to do it quickly. So it's exactly what this is. The region could be arbitrary polygon, and you are the point. And you don't want, the polygon could be very complicated with thousands of little edges all over the place, and you want to know quickly where you're at. So any kind of GPS system uses this all the time. It's graphics applications. You have a bunch of objects moving around in some world, like asteroids or some virtual reality or simulation or video game, and you have some point that you want to know which object is that point coinciding with. Now it's a 3D version of this. And you want to know quickly, because there could be thousands of objects, and each one can have thousands of surfaces or segments in it, and there could be millions or even billions of details, and you don't want to go through the whole list every time you want to find out if a point is in some object. And so now we're talking about a 3D version. So in 3D version, look how, one test of a generalizability of an algorithm is if it can, be taken to a higher dimension without too much intellectual difficulty, right? So how would you generalize this to 3D? What would the slices look like? They'll be like cylinders, right? You'd slice in the X, and then you'd slice in the Y, and then in the Z direction, you'll have 3D trapezoids, so to speak. Right? The trapezoids, what would they look like? Well, they would look like boxes on four sides, but at the top and the bottom, they'll be sliced arbitrarily at some weird angle. It would be like three-dimensional trapezoids, all stacked up in all these vertical slices. How many can imagine that and see that without a picture? Okay. What will the search look like? You search for the X, you search for the Y, you find the vertical three-dimensional slice. Within that, you have all these three-dimensional trapezoids. You do a binary search like before, and you got it. So there's the 3D generalization, and you can do it to arbitrary dimensions. Yeah.
What does n represent?
So n is the total number of vertices in the original blue polygon. So when I give you a polygon, what's the complexity of it? Well, how do you uniquely describe a polygon so it's completely unambiguous to whoever you present it to? You have to list all the vertices of the polygon, and you have to list them in order. If you don't list them in order, that's not unambiguous, that's ambiguous. If I just give you the points of a polygon, I don't tell you what order they're in. You can draw several different polygons through that set of points. How many can see that or imagine that?
Can you use line segments?
Yeah, you can give the segments. You can give all the segments, but again, in order, so that it's clear. If you do it with segments, you don't necessarily need to give the order. The order can be inferred from the segments. Never mind that now. If you knew that, that's great for you. If you can't see that, think about it. I give you a bunch of segments, and I said those are the sides of a polygon. A polygon is uniquely determined from the segments. How many believe that or can see that or imagine that? How many know what I'm talking about at all? Okay, I just want to make sure you're listening, understanding. Okay, thank you. It's called a calibration, reality check. But if I give you the points of the polygon, you don't know the order necessarily, unless I say the order in which I'm giving it to is the order around the boundary of the polygon that these points occur, that these vertices occur. Well, let me illustrate that. Example. It's always good to have examples. So, if I have, say, these, let's put these points. It's like there's a polygon. I just give you the points. Well, where's the polygon really? The polygon could have been, something like this, or it could be something very different. You can see there's lots of ways to connect these points into a polygon. Yeah, I didn't have to do it this way, right? Just to give you a quick example, I could have done it that way right there, and many other places. There's a lot of ambiguity there. But if I give you all the pairwise segments, you can convert them to a total order around the perimeter. Okay, so let's leave that at that. Okay, any other questions? Yeah. Yeah, so the vertical slices are induced by the x-coordinates of the points that induce those slices. Within each slice, I'm sorting the trapezoids by their height or by their y-coordinates. So obviously, the yellow is above this red, and there's no two ways about it. You can't just flip them and say it's the same thing. And this red is above this yellow, and so on. So this one is below that one, and this one is below that one, and this one is below that one, and so on. So another way of saying it, sort their centroids by the y-coordinate of their centroids. That's kind of a roundabout way of saying it. But you don't really have to compute centroids here. You just have to look at the y-coordinates of the left sides of all the trapezoids and sort by that. That's all. But the point is, there's a total ordering imposed by this scheme. It's important that there be a total ordering here. What's a total order, by the way, as opposed to a partial order? Some orders are not total, they're partial. What's a total order? It's not a tough question, but I just want to make sure you understand the definition. Yeah?
Every element can be compared and we have.
Yeah, every element is uniquely comparable to every other element in a less than or greater than unique way. Some element, no two elements are incomparable to one another. Okay. So squares can be totally ordered by their area, for example. The bigger the square, the bigger their area. No two ways about it. A bigger square can circumscribe a smaller square. A smaller square can lie inside a bigger square. Squares can be totally ordered by their area, or the length of their side, which is equivalent, because the area is just the squares of those things. Rectangles cannot be totally ordered by their area, in terms of one being able to fit inside another. So if you have a rectangle with a very small area that cannot fit inside another rectangle with very big area, how many can imagine that? Yeah, of course. That one that's very narrow like a needle, but a mile long, and that cannot fit into 1 square centimeter rectangle that has some square centimeter area, but a mile long, very thin rectangle has like square millimeter area, but it doesn't fit. So those cannot be totally ordered. So there's many other examples you can use, but let's back off from that. So here everything is totally ordered, which is nice. Any other questions about it? Because we're going to go deeper into this kind of analysis and get more and more esoteric. Yeah. Very good question. In the pre-processing step, how can you tell if the trapezoids are red or they're green when you pre-process all that stuff? Excellent question.
So since you know the boundaries already, the figure or the diagram, you know the polygon, you have the upper bound, you have the lower bound, and anything with the above the lowest lower bound and the lowest upper bound would be inside the what's desirable.
Yeah, when you create them, you keep in mind that some of the trapezoid edges will coincide with some edges or not necessarily edges, but segments of edges of the original polygon, the blue edges. So some of the greens and the reds will overlap with the blues. And when they overlap, that's when it flips from inside to outside and that kind of thing. So part of the pre-processing step is you detect those overlaps and you note them. You record them for future reference. And how do you do that efficiently? I'll leave it up to you to think about. But it could be done within the pre-processing time. It's not that onerous. Yeah.
I thought that always like external interior instead of this should be this one. Is it true? That the order that we know that all external.
Yeah, that's a simpler way to say it. If it's an even polygon, like the 0th polygon is exterior, number 1 will be interior, number 2 will be exterior, and so on. It'll alternate. You're right. But then, how do you know which one is even and which one is odd? So the question then becomes that. So all I'm saying is you can do that reasonably well within the original n squared pre-process, because you have a lot of time to pre-process. It's n squared time to pre-process. So you can compare, everything in a strip to everything else in a strip, and you still won't be any worse off for it. And by the way, let's in a minute we'll see why it's n squared. Well, first of all, you see that n squared is enough for the space requirement. There'll be at most n squared trapezoids resulting from this scheme. How many can see n squared trapezoids in the worst case? Nobody's raised, or a few people are saying, okay. We'll come back to that question in a couple of slides. But for now, let me just say there'll be at most n squared trapezoids. I mean, the simplest reason is that when you run these slices through, how many vertical slices are there? Each one goes through one of the endpoints of the original polygon. So how many are there? N. Each vertical slice can cut through, at most, in the worst pessimistic case, through how many edges of the blue polygon? I hear 2. Could it be more than 2? Let's see, yeah, it could be more than 2. Yeah, it's a non-convex polygon. So how bad could it get? One vertical line can slice through how many of the original blue polygon edges? Order n. I mean, you can see it could be as bad as n. Let me show you an example. So I'm going to skip ahead. I was going to show it a little later, but since we're talking about it now, let me show you a worst case example. Skipping quite a bit here. We'll come back. Okay, here we go. So here's the geometric kind of scenario. We're trying to figure out point location inside arbitrary polygons. In this case, it's geographical areas on a map. All right. The worst case. Here is a zigzagging polygon. This is a polygon with n edges in green here. Okay. N over 2 of the edges are right there. The zigzag line contains roughly n over 2 of the edges. And then the other n over 2 of the edges are zigzagging the long way around, the horizontal here. That's the polygon. You'll see in a second why I'm choosing this weird looking polygon to illustrate the lower bound of n squared. Now, when you take these vertical slices, like we did before, each one of these little edges here will introduce a vertical slice that will slice each and every one of the other n over 2 horizontal edges. So there'll be how many trapezoids here total? Roughly, asymptotically. N squared, right? There's a number of subregions. These are all the trapezoids, right? That's a trapezoid, that's a trapezoid, that's a trapezoid, that's a trapezoid, that's a little skinny trapezoid. There's another trapezoid. How many trapezoids in total do we have? Well, n over 2 times n over 2, which is n squared over 4, which is theta over n squared. So that's a worst case example. And it won't get any worse than that. Why won't it get any worse than that? Because each vertical, so it could be at most n vertical slices by definition. If all the x coordinates are unique, there's n vertical slices. If some of the x coordinates are not unique, it could be less than n vertical slices because the x's may not be unique, but it could be at worst n vertical slices. Each slice, in this example, cuts through all the other edges almost asymptotically. That's about as bad as it can get. It's not going to cut through anything other than what's already there. There's n edges there, there's n over 2 edges there that it's cutting through. Asymptotically, that's worst case behavior. N squared trapezoids in total that are induced by this scheme. And that's a lot of trapezoids, but that's all they're going to be. They're not going to be more than n squared. Yeah.
That doesn't scale 3 dimensions though? Does it?
How does it scale to 3 dimensions? 3 dimensions, what will this number be, do you think?
Just n to the d?
Yeah, but let's say for 3 dimensions, n cubed, it'll be n cubed. How many can sort of intuit n cubed in 3 dimensions? Yeah, that's what will happen in 3D. And in a dimension d, it will be n to the d. So I'm not saying this scheme is the greatest for higher dimensions, because it grows exponentially with dimension, but for a fixed dimension like 2 or 3, it's n squared or n cubed, but not more than that. It's not exponential. There's actually better schemes than that. I'll talk about it in a second. But this works. It's basic, does the job. It's well disciplined. It's generalizable. So n squared theta of n squared space is required. It's both necessary and sufficient, because you can store all these trapezoid in n squared space. There's n squared of them, and you're sorting them by x coordinates first. And within each one, the strip contains at most n. And again, that's a sorted list. And you can do all this sorting also in n squared time. You're doing sorting over and over again for every strip, but you can pool your work. You don't have to resort everything from scratch every time you create more and more trapezoid. So I'll leave it up to you to see how all the sorting together can be done in n squared time as well as n squared space. Because if you weren't careful, you may have taken you n squared log n time to do n sorts. How many can see that? You're sorting n things n times. Sort n thing is n log n. With n times is n squared log n total. But you can do n squared total by pulling together all the work and not having to resort repeatedly unnecessarily. And here's what I was alluding to earlier. You can be a lot more clever than this. This is a basic scheme that works. It's easy to see that it works. But if you want to, dive deep into the subject matter and be more clever and use very esoteric data structures and a lot more complicated analysis and very tricky preprocessing, you can get the space to linear. The preprocessing time will drop to n log n, and the query time will remain logarithmic. You can do all that. I'm just letting you know. For extra credit, you tell me how. But it's too complicated to explain in class. It just wastes too much time, and the value will be limited. So let's leave it at that. But I'm just telling you, you can do a lot better than what I just showed you. But what I showed you works. And it works pretty obviously. And the data structure is very simple. It's just arrays, sorted lists of trapezoids, and it's just binary searches, and nothing too esoteric about that. Yeah. But don't think this is the best that's possible. It's probably been for many decades now, and better and better solutions for it exist. Any questions about the worst case behavior? So obviously, this scheme that only uses linear space doesn't use trapezoids like this. Because if it did, this kind of worst case example would already blow up the space way beyond linear to quadratic. So obviously that scheme that I just mentioned but didn't detail for you doesn't use just plain trapezoids. It's such a wasteful matter. That would still blow up quadratic. All right, so backing up the slices that we skipped over. So we did point location, and now we did this trapezoid method, and sometimes it's called the trapezoid method actually. We do a lot with that kind of reasoning and technique. It's not just for point location. Many other things are sort of like trapezoidal-like subdivision of configurations into arbitrary tiny slices. So let me show you another problem, very similar, but more general problem that this trapezoid method solves. So let's say you have not just a single polygon, but multiple polygons. Let's say you have these 3 polygons, which is like a geometric kind of partition of the plane into all these regions, like a geographical map of the United States, into counties or states or whatever, or map of Europe divided into countries, and these are the outlines of the country. And now you just don't want to know if a point is inside or outside a particular single polygon, but you want to know which polygon is a point inside of, or is it outside of all the polygons, completely outside all of them. So the query point comes in, and you allow pre-processing, so there's different regions, region 1, region 2, region 3. You want to know if this query point or that query point is in the interior of which region, 1, 2, 3, or outside all of them, completely in the exterior of all the regions. So the solution to this is very much almost identical to the solution we just saw to single polygon point inclusions. How? Well, create vertical slices through all the polygon vertices. And by the way, here n is the number of vertices in all of the polygons added up. So it's the number of vertices in the entire configuration, not just one of the regions, but all of them together. So put vertical points, vertical slices through all the points, all the vertices of all the polygons in blue. Then create these trapezoids again, like we did before. And as you create these trapezoids, sort them within each vertical strip or slice by their y-coordinates, like we did before in the previous problem. And once you do that, when you have a query point, you take the query point and find out which slice it's in, then find out which trapezoid is in within the slice, and these trapezoids are all labeled with different regions. These are all the region 1 trapezoids in green, these are all the region 2 trapezoids in gray, and these are all the region 3 trapezoids in blue, and all these are exterior trapezoids in red. And once you locate a point within the right trapezoid, you'll know which region it's in, or whether it's in any one of the regions, and just outside by being in a red trapezoid. It's exactly the same solution as before, except it's solving a more generalized problem. We have multiple regions, not just one. How many can see that this works just the same as it did before? Okay, any questions about that? This is the power of this technique. And again, you can generalize this to 3D and do arbitrary number of 3D regions and so on. Yeah.
So initially in single trapezoid case, you can easily tell like the alternate sequence that was coming out, like which trapezoid was. But here, as we can see, the sometimes you can see the blue, then black, then again blue can be there.
Yes. So here it's not just as simple as odd, even, inside, outside, because there's multiple regions. But you can keep track of that as you pre-process, and you can still do it in quadratic time. I'll leave it up to you to figure out all the details of how that would work. But you can do that in quadratic time and quadratic space. Very similar to before. But that's a good point. You know, if you had to program this, you have to figure out this little detail of how to label trapezoids with the right colors so that it's obvious which region each trapezoid belongs to. So when a query point comes by, you can quickly determine that, and not just start doing a long computation of that. All that's part of pre-processing. Generally, whenever you allow yourself n squared pre-processing time, and even n squared pre-processing space, it's very generous. You know, there's a lot of slack built into those bounds that you can do a whole lot of pre-processing very comfortably without even straining yourself too much. You know, with clever shortcuts and optimizations. N squared is a very loose bound on pre-processing time and space. N log n is a trick. N log n is not much breathing room before you exceed it in terms of time, never mind space. But n squared, you can do a lot in n squared. Okay, any other questions? All right, so just so you don't think there's something magic about these vertical slices, let me show you an alternate scheme of slicing that's not vertical. So here's a point inside or outside. Again, we'll do it for a single polygon, but you'll see how this generalized to arbitrary sets of polygons in the region, set of regions. So what we'll do is we'll pick some point inside, and we'll slice by shooting rays out to all the vertices of all the points on the boundary of the polygon, all the vertices of the polygon. So the slicing scheme now will be like a pizza pie, but more complicated. Right? And each one of those slices will have lots of trapezoids. One trapezoid in green, another one in red. Here it'll be green, red, and red again. So now we're alternating green, red, because you just have one region. And you can see how that will work. And so to figure out if a point is inside or outside the original blue polygon, first look at which slice it's in. The slices now are wedges. They're no longer just vertical strips. They're arbitrarily angled wedges. But you can do that using what? Binary search. You're getting a lot of mileage out of binary search at all levels. And once you figure out which wedge it's in, just alternate green, blue, green, red, and then you sort by the distance in the wedge. These trapezoids are sorted in a total ordering inside each wedge, just like they were in a strip, except instead of a strip, it's now a wedge. And then you'll know whether it's inside or outside. So 2 binary searches will get you that. 1 binary search to find the wedge, and then within a wedge, do a binary search to find the trapezoid. And based on the color of the label of the trapezoid, you know whether you're inside or outside. And all this is happening in the pre-processing. So I just want to bring it to your attention that the fundamental thing about this scheme here that we saw before is not the fact that these are vertical strips. That's almost irrelevant. It's the fact that you're partitioning it into 2 sets of ordered objects. One is ordered by some parameter and the other is ordered by some orthogonal parameter. And you're doing a pair of binary searches. That's the crux of the scheme. That's the essence of this scheme. It's not the vertical strips. Because you do the vertical strips, or you can do it with wedges. Or you can do it with many other geometric arrangements. It didn't even have to be that. It could be something else altogether. And it would work just the same. Pair of binary searches. And all these things generalize binary search to 2 dimensions. Because if I want to know between which 2 numbers a number falls in, and I can sort the numbers, pre-process it by sorting them, and then binary search will tell you between which 2 numbers my new query number falls in. That's binary search in 1 dimension. This is binary search in 2 dimensions. And we can generalize to 3 dimensions. And it's not easy to generalize to higher dimensions. Now I can appreciate binary search even more. Because generalizing it to 2 dimensions or 3 dimensions, you see, it's not trivial. You have to come up with some scheme that will make it work and keep the time to logarithmic. And the pre-processing could take a while. Any questions about this alternate scheme or other schemes and the essence of the solution? It's not about vertical strips. That's just scaffolding. You can use other kind of partitioning schemes as well. Yeah.
On the previous slide where you had multiple polygons with it,
Right here?
can the other the more efficient algorithm generalize to that as well?
Yes. Yeah. So this algorithm that I mentioned earlier,
That'd be useful.
those previous slides. Yeah, right here. Linear space and n log n time. Yeah, he generalized to arbitrary planar subdivisions. So this thing here. This thing here is called a planar subdivision. Why? Because you're subdividing the plane into regions, like a map does. So it's called planar subdivision search. And yeah, what he said, the previous solution that I mentioned, but didn't explain because it was too complicated, linear space and n log n preprocessing and still logarithmic query generalizes to planar subdivision. It certainly does. And there's the worst case example, we already been to that. So bottom line is log time per query, and n squared space, n squared preprocessing time, that's what we've seen, we've shown, we've just analyzed that. And I mentioned that linear space and n log n time preprocessing suffices with a much more complicated scheme. And that's true for a single polygon, that's true for many polygons for arbitrary planar subdivision as well. And there's methods that are efficient in higher dimensions. In higher dimensions, linear space law is no longer enough. You need some space that grows with the dimension, with the dimensionality of the objects. But let's just leave it at that. Keep in mind that in 3D, objects could be very complicated. There's a bunny rabbit that has, I don't know, thousands and thousands of edges and facets around this big polygon that's the rabbit. And in video games, everything is a polygon or a polytope. Nothing is really round. Think about it. It's just that the objects in a video game or virtual reality or animation sequence of a movie, there's so many polygons that it looks round, but it isn't. Just like if you look at your smartphone screen, you just see continuous images and beautiful sunsets, but everything is just pixelized. There's no continuous anything on the screen. Everything is a pixel. But there's so many pixels, there's more pixels on the screen than you have rods and cones in the retina of your eye. So your eye is not even sophisticated enough to see all the pixels. That's why it's called retina display for the smartphones, for the iPhones, and now every phone really has a retina display, which means it has more pixels on the screen than you have rods and cones in the retina of your eye. So to you, everything looks continuous, but really everything is polygonized, polytope, and pixelized inside the computer, inside the simulations, and even on the displays. You just lose track of that because it's such fine detail. So many of them are so small, they works out. That's why query times of logarithmic are important, because there are objects in video games that have millions and millions of points and polygons. They're very complicated objects. And when Pixar and Disney produce animated films, some of their characters have billions of polygons. Every hair on the animated body of Monsters, Inc., or any one of those sophisticated characters, Frozen, or any one of your favorite characters in animation, they have billions and billions of polygons. And they're all moving independently. And they have physics engines that simulate gravity and shear of wind flow. And it looks fantastic. At the end, it looks photorealistic. But it's all made of polygons. All of it. Okay, any other questions? All right. So, speaking of polygon, here's a simple polygon. Simple means non-self-intersecting. Doesn't mean it's not sophisticated polygon, but it looks familiar. What does that look like? You squint your eyes, kind of. Everybody recognizes this? Mona Lisa, right? Where's the Mona Lisa right now? Museums, the Louvre, right? So if I give you a point in this polygon, and by the way, this is a continuous tour. It's a simple polygon, non-self-intersecting closed loop. It's just warped in a way that makes it look like a Mona Lisa. But if I say, is this point inside or outside this polygon? I'm going to say it's inside. I'm going to say it's outside. So it's not obvious, is it? Right? And that's why you need algorithms like we just saw. Because when things get hairy, and this is not even a huge example, it's just a medium-sized example, it's not obvious at all. And you don't want to look at the entire, 10 million segments to figure it out. You want to do it in logarithmic time after some pre-processing. So here's an example where it's not so obvious, the inside and the outside. I'll give you another example. Here's another polygon. Looks familiar? Yeah, where did you see that? Sistine Chapel, right? This is, who's the artist? Which artist drew this on the ceiling of Sistine Chapel? Yeah, Michelangelo. Yeah. And if I give you a point again and say, okay, is this point inside or outside this polygon right there? It's not so obvious. And here's one that's also famous. This is it's not just a tomato soup can by Campbell. It's also a famous piece of art. Who did this? Andy Warhol. At UVA, we promised you a classical education. By golly, we're going to give one. So again, a point somewhere in here. Is this inside or outside? Hard to tell. So one relatively easy heuristic is I can paint the inside with a color. So here I painted the inside of this polygon with red. Now you know if the point is inside or outside. It's outside because it's in the white. But before that, it wasn't easy at all to tell until I painted it for you. I want to see it again in slow motion. There we go. Never mind how long it took me to create these beautiful slides for you, but It's one of my hobbies, my gift to you. So there's these polygons that can look like interesting things, and this brings a project idea out. So I'm mentioning now, we talked about the project at the beginning, and you don't have to do this particular thing, but this is one possible project idea. Is take a rasterized image, an image, any picture, any photograph or painting or GIF or JPEG or TIFF file or whatever is an image, rasterize it in a way that they then create a traveling salesman tour, which basically is a polygon, a simple closed polygon through all the points. It doesn't have to be the shortest one, it could just be one that doesn't self-intersect, and that's good enough. And then that will resemble the original image if you pixelize it just right and you do the right thing. So from an image that I give you, you give me like a polygon that resembles the original image. And you can use colors, this is all black and white, but you can use colors to paint the edges, and then the colors too will resemble the original. And think about how you do all that algorithmically. And so optimal traveling salesman, of course, is NP-complete. We'll get to that when we talk about NP-completeness. But for now, let's just say you can use heuristics, very quick heuristics, to create such beautiful images. And it's not that complicated, actually, conceptually. How many can see how you would program this? Just a few, 3 people, 5 people? Okay. Well, good. Then also you might want to do this project then, and you'll learn a lot. But it's not that hard. You convert the image to a black and white set of pixels, and then do some sampling to, pick some points and not others. Otherwise, there'll be points everywhere. It'll be too dense. So thin out the cloud of points. Do some averaging technique, like in every 3 by 3 grid of pixels, take the average of all. The middle point will be on if there's less than 5 of the 9 are on, and it will be 0 if. It would be 1 if more than 5 are on, it will be 0 if less than 5 are on. Now you're thinning out the image into a cloud of these few pixels with some spaces in between. And now you can connect them all to a polygon after you create this point set using some TSP, traveling salesman problem heuristics. And it doesn't have to be optimal because it's NP-complete, but you can very quickly create some nice tours through it, and they'll begin to resemble the original image, and you can play with the thickness of the lines and the colors and so on to make it even more interesting and artistic. And, you can create an image like that for your parents' anniversary based on one of their photos from their youth, and they're going to love it. Especially if they can appreciate computational geometry algorithms, they're going to love it even more. But one thing for sure, they'll know you didn't get it on eBay. You know it was a labor of love that you created yourself, because it's very specialized and it's mimics the original picture. So it's not something you get arbitrarily on Amazon or eBay. It's something that you obviously created. And you can create an app based on this and put it on the web and allow people to use it and experiment and have different parameters, color scheme, and pixelization, of the image into points, and using various heuristics to connect things and play with the line thicknesses, and you can make a beautiful kind of app using this. And you don't have to use a tour. You can create a minimum spanning tree over these points, and it'll still resemble this kind of image. How many can see that? If you do a minimum spanning tree, okay, let me not be presumptuous. How many know what a minimum spanning tree is? Okay, good. So if you have a cloud of points that resembles, the density of the points resemble the gray value, the grayness value of the original image. If you do a minimum spanning tree on that, the tree will have similar densities as the original point set, and that will mimic the grayscale value of the image. And the minimum spanning tree will look like the original image. How many can imagine that? Okay, if you can't, maybe look up some examples on the web, or just program this, and you'll be fascinated and amazed when you see the results. It's very artistic. Any questions about this project idea? It's just an idea. You don't have to do this, you can do other things, but if you're so inclined and you want to play around with algorithmic art, let's call it that, here's your chance. Create some beautiful thing. Any questions or comments on this? I posted another project on the website, a sample project having to do with puzzle solving, arbitrary tiling kind of puzzles. How many have looked at that? Okay, good. That's another thing you can do. That's kind of interesting. I'll bring some examples of plastic puzzles I have, just like the ones I showed on the web, that I'll pass around and you can see how it actually looks when you buy them on Amazon, and all the plastic pieces that you have to fit in a nice square or grid. But you can write a program that solves those automatically. With every different project, don't do Sudoku, please. It's been done so many millions and tens of millions of times, and so predictable, and that'll be kind of boring. So don't do Sudoku. Like sometimes you walk into a guitar shop, a musical instrument guitar shop, there's a big sign that says, you can use the guitar, but please don't play Stairway to Heaven. Because that's what everybody does. Okay. Here's an interesting question. So talking about simple closed curves, tours, or polygons. Does every simple closed curve contain on its boundary somewhere 3 points that are the vertices of an equilateral triangle? That's the question. So for example, here's an ellipse, and by the way, they don't have to be a polygon. It could be smooth curves, not necessarily polygonal curves, but particularly, you can use a polygon. But for this ellipse, are there 3 points that give you an equilateral triangle? And here's one set of 3 points on the boundary, all three are on the boundary, that together give you an equilateral triangle, all three sides of it. So it's true for an ellipse. Is it true for some arbitrary shapes? Is it true for this heart shape? Is it true for other strange, irregular, arbitrary shapes? That you can always find 3 points on the boundary that give you an equilateral triangle. Is it true for this Mona Lisa? Are there 3 points there that give you an equilateral triangle? Is it necessarily always true for every simple closed curve? Yes or no, and why? Prove it one way or the other. How many understand the problem? How many have a solution? Nobody. Good. Well, I'm glad I didn't insult your intelligence. And another one of my gifts to you. So work on it for extra credit. See what you come up with. So that's a question about simple closed curves, and also about polygons, which are simple closed curves. So it's a question about any simple closed curve. So either prove that it's always true, or find me some counterexample that it's not true. Okay, and this brings us to convex hulls. Any question about anything we've done so far? So we're going deeper and deeper into computational geometry, geometric algorithms, and we're going to get more and more esoteric as we go. And now we can use the stuff that we've seen before as subroutines. So now when I solve a more complicated problem in computational geometry, say, remember the planar subdivision search? We're going to use that as a subroutine to do this, and here we go, keep going, and we're going to build on what we've done before. That's what computer science is all about, calling subroutines. You couldn't call subroutines computer science really very useful. Think about it. All right, so what's a convex hull? It's the smallest containing convex polygon for that point set. So I give you a point set, and the convex hull of that point set is the smallest area convex polygon that contains all the points. So in this example, it's this one. And you generalize to higher dimensions. In higher dimensions, this polytope again is a 3D generalization of polygon. This polytope contains all the points in its interior. And there's lots and lots of applications for this. Gaming and collision detection and graphics and simulations and video games and animation, movie animations. And so for example, if you're running some simulation like that, or it's either in virtual reality or a video game or just molecules bouncing around, whatever, and you want to know when these things collide. And each object could be millions of points or polygons, but when two objects collide, you want to detect that. So generally, you want to test every polygon of this object against every polygon of that object, and that's a lot of testing every time they move one pixel in some direction. That will never happen. It's too computationally intensive. What you can do is compute the convex hulls of both of them. And if the convex hulls don't overlap, the objects haven't collided, or the objects don't overlap at all. If the convex hulls don't overlap, how many can see that? Yeah. If the convex hulls overlap, doesn't mean that the objects overlap, but if the convex holes don't overlap, the objects don't overlap, and non-overlap is the usual case. Collisions are rare. And on city streets, thank God collisions are rare. The convex hole will contain a lot less points than the actual point set. The point set can have millions of points, but the convex hole could just be 50 of them. And that's only have to test for collisions against other objects instead of looking at all millions of other points inside. And so I'm just giving you a scenario where a convex hole subroutine will be very useful in scenario of collision detection, especially of multiple objects. Yeah.
What's an example where the convex hulls do intersect but they don't collide?
Oh. There's an example right there. The convex hull of my hand will be the entire glove around my hand. So my fingers don't intersect, but the two gloves will sure intersect. The gloves are the convex hull. You can imagine that. Okay, so lots of examples, yeah.
Are we always guaranteed to have a convex polygon for any group of points?
Yes. So very good question. He's asking what guarantees us that there'll always be a convex polygon containing all the points. Maybe there will be a polygon, but it wouldn't be convex. Very fair point. That's actually a theorem. It needs to be proven. Let me prove it to you this way. Every pair of points define a half space. This pair of points here define a long line that contains the segment. Half of that half space is a half plane. So the rest of the points will be contained on this half plane, not on this half plane, given that the half plane is defined by this segment. So everybody with me so far? Okay. Same for this. Same for this. Same for this. Same for any other pair of points, even the interior ones. But for the interior ones, if you put a half plane through a pair of points, not all the points will be on one half or the other. Some points will be on one side of the half plane, some points will be on the other half of the half plane. But for the boundary of the convex hull, all the other points will be on one half and not the other. That's what defines actually the convex hull boundary. But let me say this. The convex hull is the intersection of all of these half spaces that are defined by boundary points. And a half space is a convex shape, even though it's semi-infinite. The intersection of two convex polygons is another convex polygon. Convexity doesn't change when you intersect them. How many believe that? Not necessarily you can see the proof, but believe that the intersection of two convex figures is another convex figure. It's true. So the convex hull is the intersection of all the half spaces defining the periphery. And the intersection of all these half spaces, all of which are convex, is also convex, and there's your convex shape containing all the other points. That's the essence of the proof. You can work out some of the details and stuff. Since you asked, and that's why there's always such a thing. It always exists. But that's a very good question. Why must it always exist? This is why. Because it's the intersection of all the half spaces that come from infinity and touch the point set. The intersection of all of them is the convex polygon. And the intersection of convex sets is a convex set. It's true not just for polygons. It's true for arbitrary convex sets in arbitrary dimensions and arbitrary metric spaces, actually. Not just Euclidean space. Okay, so how do you compute the convex hull, the convex polygon containing all the points? It's not obvious at all, especially if you want to do it efficiently. So how do you do it? Well, lots of ways to do it. Here's the first algorithm. We'll see half a dozen algorithms for this. This is sort of the analog of sorting for computational geometry. There's lots and lots of ways to sort, lots and lots of ways to do convex hull. So find the leftmost point. How do you find the leftmost point? Find the one with the least x coordinate. That's the leftmost point. And then start rotating it until it hits one of the points in the set. So rotate it like this until it hits this next point. Okay? And you don't literally have to rotate it continuously. You just compute all the angles to all the other points and find the one that's the least angle given your orientation right now of the current segment. How many get that? So I can do it in a discrete way, not intuitively. I'm sort of showing it continuously, but just conceptually. All right, now anchor it over here. That's your first convex hull edge. Now repeat this process right there. Draw this green line going out, and then rotate that green line until it hits the next point, and that's your next edge of the convex hull. And you can see how this is going to go. Right? Take this new segment, extend it out in green, rotate this green until it hits the next point, and that's the new edge, the next edge of the convex hull, and keep going. How many can see how you'd implement this if you had to implement this? Okay, pretty straightforward. And again, notice that it's not continuous really in your algorithm. It's test them all and get the one with the least angle. So if there's one with this angle, this, take that one first. And then start here, repeat the whole process there, and then repeat the whole process there, and that's what you get. So that's another way of saying it always exists, because this gives it to you on a silver platter. And obviously, it will always produce something. It will always produce a polygon containing all the other points. Okay? So just to finish it off, it just keeps going. Any questions about this algorithm? That's it. That's the algorithm to compute a convex hull. There's much faster algorithms than this, but we'll get into that. Yeah.
Is there only one convex hull?
Excellent question. So he asked, does it exist? He's asking the follow-up question. Once we know it exists, is it unique? Do there exist many convex hulls, all different than one another? Not by the definition of convex. Convex hull is the smallest one, the one with the least area. That one is unique. Because lots and lots of other polygons will contain all the points, but they wouldn't be the smallest. Right? I mean, Europe contains France, but Europe is a lot bigger than France. It's also not condensed. Never mind that. And this keeps going until you get the polygon. And when does it end? When the next edge includes the original point where you started. Now, originally we started with the point with the least x. Do we have to start there? Would we have started somewhere else, for example? Would we have started with a point with the largest x? How do you say, yeah, sure. How about the largest y? Sure, you could have done that too. The smallest one, yeah, you could have done that also. Lots of places where you start. But you don't want to start with an arbitrary point that's in the interior. And that's why we put the starting point at an extreme point. An extreme point meaning with the largest x or the smallest x or the largest y or the smallest y. That's guaranteed to be on the convex hull. How many see that? Yeah, that's why we do that. How fast does this run? By the way, this is called the gift wrapping method. How many can see why it's called the gift wrapping method? Yeah, because when you wrap a gift with wrapping paper, you're sort of doing this algorithm in 3D. And at the end, the shape of your gift will be the convex hull of that thing, whatever it is. It may not resemble very closely the original thing in some cases. But if you gift wrap a car like that, other than the fact that the wheels are sticking out, yeah, you can sort of tell by the shape of the convex hull something about the object itself. Right? If you see a mummy all wrapped up, you know there's some dude in there. That's the mummy, right? Actually, that's not a convex hull because it's got all these appendages hanging off of it. But never mind. The point is, from the wrapping of the gift, you can sort of tell what the gift is. Of course, sometimes it backfires. If you wrap a bicycle like that, it probably won't be able to tell it's a bicycle very, very easily, or maybe you could, I don't know. But the point is, it's called the gift wrapping method because that's sort of how it works. That's how it works in 3D also. Let's say the number of vertices in the convex hull is h. At the end, there's 1, 2, 3, 4, 5, 6, 7 vertices in the convex hull. Call that number h. The running time will be n times h. Why? Because for every new vertex in a convex hull that you're rotating the line from, you have to test at worst all the other vertices to see which one has the least angle, and then pick that one and repeat, repeat, repeat. By the time you're done, you've done that how many times? Well, however many times there were vertices in the convex hull. That's how many times you repeated this process, scanning through all the other points, n of them. So the total time is h times n. How many can see that? H is the whole number, is the number of points in the convex hull. Now, how big can h be with respect to n in the worst case? Not a trick question. Easy. How big can h be as a function of n? N. It could be absolutely equal to n. If all the points on the periphery of a circle, the convex hull will be all of them. How many can see that? There'll be no interior points. So nh could be n squared, but it can also be much smaller. If all the points are inside an equilateral triangle that only has 3 vertices, and all the points are in the interior, and there's 10 billion points inside the triangle, h will still be 3. And the running time of this will be almost linear. It will be 3 times n. It wouldn't be a billion times a billion. How many can see that? So this algorithm has a nice property that the runtime varies with the size of the output. And the smaller the output size is, the faster this will take to run when it reports the convex hull to you. So it's output sensitive. So some algorithms are output sensitive, and this is one of them. Some sorts were output sensitive, or even input or order sensitive. Some sorts that we saw, sorting algorithms, dependent on the order of the input, and they run quicker if the input was already sorted. How many remember that? Like bubble sort. Other algorithms were inversely sensitive to the ordering of the input. If the input was ordered, it ran in terrible time. How many remember that? What algorithm did that? Terrible if it's already sorted. It's like quick sort, or any one of a number of them, actually. It's in reverse sort. And this generalizes to higher dimensions, and it parallelizes nicely also, because you can do this at different places. You're using different processors or processes independently of each other, and you get different sections of the convex hull, then you merge them all together. So it parallelizes nicely. Not all algorithms parallelize nicely. And it's the analog of selection sort. How many can see that? Because at every phase, you select the next one that has the least angle compared to all the other ones. That's what selection sort does. Selection sort always selects the next element that has the least among all the remaining elements. That's exactly what this does, except using polar angles as the measure of least. How many can see that? It's selection sort analog for convex hull. And we'll see other analogs for sorts in convex hull scenarios. We'll see an analog of quick sort for convex hulls. We'll call it quick hull. And we'll see an analog for merge sort for convex hulls. We'll call it merge hull. And so on and so on. And now you'll see why we harp so much on sorting, among other things. They're translated to very nice analogous situations for other scenarios. Very nice, including divide and conquer and the whole 9 yards. Any questions about any of that? So now we're deep into convex hulls. We'll see more algorithms, and then we'll see a really beautiful algorithm for convex hulls that will really blow your mind. It'll be amazing. So in the book Corman, there's a whole chapter in computational geometry. So start reading that, and of course in Preparata and Shamus, that book about only computational geometry that I put it on the collab. There's a whole section, a whole chapter on convex hulls. So start digging into that as reinforcing materials. Any more questions? Comments? We're all good? All right. See you next time.
Sharp algorithm.